Just imagine, you're hurtling through space chasing after a beam of light. But try as you might, you can't catch up. That's because light is the speed demon of the cosmos, the ultimate racer with no rival. But why does it hold this prestigious title? And what secrets does its velocity hide within the fabric of the universe? In this journey, we'll unravel the mysteries of light's speed, exploring its significance in the vast expanse of space. From the birth of stars to the dance of galaxies, light guides us through the cosmic symphony, revealing the wonders of the universe. So, buckle up and prepare for an exhilarating ride through the cosmos. And don't forget to hit that subscribe button. Back in the day, folks believed light zapped across space faster than a blink, getting where it's going the second it leaves. Seems kinda silly now, right? But think about it. How could something move that fast? Even light, speedy as it is, can't travel at infinite speed. It's like trying to catch a shooting star with your bare hands. But if you really stop and ponder, it's not such a wild idea after all. How could you even show that light doesn't zip around instantly? Now, proving that sound doesn't move at infinite speed is a piece of cake. Just get a buddy, have them bang a drum far away, and wait for the sound to reach you. It's like that moment when you promise your friend a treat to keep them happy. The delay between what you see and what you hear proves that sound isn't lightning fast. But honestly, you don't need to do a whole science fair project for this. We witness sound's finite speed every day. Think about the bang after a firework or the echo in a big empty room. Even at concerts, watch the ripple effect as music travels to the back of the crowd. It's like waves on a musical ocean. Let's rewind to 1638 when the brilliant thinker, Galileo Galilei, ventured into an intriguing experiment with light. Picture this. Galileo and his assistant perched atop two distant hills, each holding a lantern under wraps. The plan was simple. Galileo would unveil his lantern, and upon seeing the light, his assistant would do the same, signaling back. Galileo, clever as he was, aimed to time how swiftly light traveled between them, factoring in a slight delay caused by his assistant's reaction time. But here's the twist. That delay turned out to be way longer than expected, leaving Galileo scratching his head. Did light zip across instantaneously, or did it zoom at an astonishing pace? Even with Galileo's brilliance, this experiment ended in a puzzle. Surprisingly, less than 4 decades later, a revelation emerged, courtesy of Danish astronomer Ole Romer. Ironically, Romer's breakthrough stemmed from a different piece of Galileo's work. Back in 1598, King Philip III of Spain threw down a challenge: find a way to measure a ship's longitude when it's far from any coastline. Fast forward to 1616, where Galileo stepped up to the plate. Fresh off his discovery of Jupiter's moon, Io, he proposed a clever solution using the moon's eclipses as a sort of celestial clock. Now, the nitty-gritty of how it all worked isn't crucial here. What matters is a curious observation made later by Ole Rømer and astronomer Jean Piccard regarding the timing of these eclipses. Rømer caught on to something peculiar. The time between eclipses seemed to shift depending on the season. Why? Well, as Earth and Jupiter danced around the Sun in their orbits, they sometimes drew closer, sometimes farther apart. Rømer connected the dots. This changing distance affected how long it took for light from Io's eclipses to reach us, and if light's journey time was tied to distance, then it couldn't be infinite. It had to have a set speed. Rømer even took a stab at calculating this speed based on his findings, coming remarkably close to the mark, within 25% margin. Over the years, countless scientists have taken a shot at getting a more precise measurement of the speed of light. By the 20th century, with the help of fancy techniques like cavity resonance and laser interferometry, we finally nailed it. Light moves at a blistering 670,616 sound 29 miles per hour in a vacuum. That's over 1 billion kilometers per hour. To put it in perspective, imagine light zipping around the Earth's equator 7.5 times in just 1 second. No wonder poor Galileo had a tough time trying to clock it with his lanterns and pulse. Here's a fun fact. Since 1983, we've even used the speed of light as the basis for measuring distance. A meter is officially defined as the distance light travels in a vacuum in 1,299,792,458 of a second. But here's the big question. Is the speed of light the ultimate speed limit of the universe? Or could something go faster? Well, there are two ways to tackle that puzzle, the practical and the theoretical. Let's dive into the practical side first. With our current technology, could we push something to exceed the speed of light? The fastest man-made object to date is NASA's Parker Solar Probe, launched in 2018 to study the sun's outer corona, the fiery aura surrounding our star, visible as a glowing halo during solar eclipses. And guess what? The Parker Solar Probe is already zooming through space at an impressive speed. By 2025, the Parker Solar Probe will hit its peak speed, a whopping 430,000 miles per hour. That's seriously rapid. To put it in perspective, a high-velocity bullet from a modern rifle maxes out at around 2,500 miles per hour, only about 0.6% of what the Parker Solar Probe can do. Even if Superman and Sonic the Hedgehog had a super speedy baby, it still wouldn't match the Parker Solar Probe. But here's the kicker. None of them, not the probe, the bullet, nor the mutant superhero offspring, can outpace light. To break it down, the Parker Solar Probe will be cruising at about 0.006% of light's speed. Imagine if light were Usain Bolt. The probe would be like a wheezing senior citizen with one leg glued to the floor. So yeah, faster than light travel? Not happening with our current tech. But hey, we've pulled off some impressive feats with objects we stumbled upon in the universe, accelerating them to speeds way beyond what the Parker Solar Probe can manage. Deep beneath the Switzerland-France border lies the mighty Large Hadron Collider, CERN's prized possession. This beast of a machine is the world's most potent particle accelerator. What's it up to down there? Well, it's delving into the aftermath of the Big Bang, poking around the mysteries of dark matter and dark energy, and it even played a crucial role in unveiling the elusive Higgs boson, aka the God particle. With its colossal 27-kilometer track, we've managed to push charged particles, like electrons, to a hair's breadth from the speed of light. But try as we might, we can never quite reach that ultimate speed, and we never will. Now let's venture into the theoretical realm, where things get a tad tricky for faster-than-light FTL travel. Here's the deal. As an object speeds up, it seems to pack on some extra mass. It's not something we notice in our everyday lives, as it only kicks in near light speed. But in places like the Large Hadron Collider, we've seen it firsthand. The closer an object gets to light speed, the more mass it gains and the more juice it needs to accelerate further. Before hitting light speed, its mass, and the energy needed to speed it up, seems to shoot up towards infinity. So, there you have it. The laws of physics throw a firm nope to superfast travel, courtesy of Einstein's genius. But hold on a sec. If light can zoom around at light speed, what gives? Well, it's all thanks to those little guys called photons. They're like the air supermodels of the universe, sipping on cucumber juice for that extra boost. But hey, don't close that tab just yet. There's a whole galaxy of space science waiting for you. Dive into our channel to uncover more cosmic wonders and explore this fascinating niche. Hit that subscribe button, stick around, and let's journey through the stars together. See you in the next video.